Okay, so to summarize this part of the chapter, for the case where the wires are fixed, the wires are not moving at all, we showed that the EMF, in general, it's the integration of the force per unit charge dotted into the elements of area around a contour. But in the case where the wires are fixed, they're not moving, then this EMF is just integration of E dot ds. So this is a specific case that applies when the wires are fixed. And we also showed the Faraday-Maxwell equation that integration of E dot ds is minus d by dt of the magnetic flux. And this applies specifically also when the contour is fixed. And now if you combine these two, you have that the EMF is equal to integration of E dot ds, and at the same time it's minus d phi by dt. So this is the equation that we use to solve problems. If you want to get the electric field, then you take this term and minus d phi by dt, and you get the electric field. If you want the EMF, then you can get minus d phi by dt also. So this equation determines everything you need to know for the case where the wires are fixed. So in general, the problems, the structure of the problems, they follow this kind of way. So the first thing, if they ask you for the EMF, to get the EMF, you first get the magnetic flux, then take the rate of change of magnetic flux with time, and then multiply by the number of loops if there are more than one loop, and that will give you the EMF. And we're really interested here in the magnitude of the EMF. Don't worry about the sign. And then here, if you want to get the direction of the current, the induced current, then you use Lenz's law. So now we have a complete way to solve problems for the case where the wires are fixed.